Hi everyone! I found this challenge from PicoCTF much more interesting than others that I did so far, so I decided to do a nicer video, or at least try it. You have the link of the challenge in the description of the video. The description of the challenge says, I forgot cookies can be modified client-side, so now I decided to encrypt them. And then they give us a URL. Okay, so if we send a GET request, we see that it returns an out-named cookie. At a first glance, it seems that the cookie is base64 encoded. We can save the value of the cookie in a variable, and then we can decode the cookie. It seems to be another base64 encoded string. Let's decode it again. This time it returns non-printable bytes. This shows that it should be encrypted most probably, and it makes sense because of the description of the challenge. Talking about the description of the challenge, did you notice the small hint? See how certain letters are written in uppercase. Okay, these letters are CBC. What a coincidence, right? It could mean that the cookie is encrypted with AES CBC mode. AES CBC mode is well known to be vulnerable to bit flipping attacks. Let's quickly check what is AES CBC and why it's vulnerable to bit flipping. Let's say we have this plain text. That could be a cookie that we want to encrypt. It contains a timestamp, an attribute called isAdmin that is equal to 0, and a username that in this case is guest. It has 44 characters, that's 44 bytes of length. In AES 128, the data is split in blocks of 16 bytes. So we will have 3 blocks of 16 bytes each, except the last one that has 12 bytes. In AES, the blocks need to be 16 bytes mandatory, so we will need to add a padding. We'll see that in a second. In order to work with AES, we need to express the input data as bytes. So we can simply encode the plain text as bytes for all of our blocks. For the last block, as we said before, we need to add a padding. In this case, we have 4 bytes missing, so we add 4 bytes. The value of these bytes is always the bytes of the padding, in this case 4. So we will have 4 bytes with value 4. These blocks are then encrypted sequentially. So we start with the first block. Each block is first XORed with the previous ciphertext block. But for the first one, we don't have a previous ciphertext block. So we need an initialization vector, IB. In this case, for simplicity, we choose one that is all zeros. Then the first block is XORed with the initialization vector. And the result of that is encrypted with the key. The result of the encryption is the first block of the ciphertext. We go for the next plaintext block. Now we need to XOR the plaintext block with the previous ciphertext block. And the result is encrypted with the key. Finally, we do the same for the last block. First, we XOR with the second ciphertext block. And then we encrypt it with the key. Now we have our encrypted blocks. We can arrange them so we have 48 bytes of encrypted data from the top row that contains the first 16 bytes to the bottom one. So let's get back again. Now let's decrypt our ciphertext. We start with the first block. We decrypt it with the key, then the result is XORed with the previous ciphertext block, but this is the first block, so we don't have a previous ciphertext block. In this case, we need to use the IB. Then we will have our plaintext again. Remember that this is expressed in bytes. We go to the next one. The block is decrypted, and the result is XORed with the previous ciphertext block. We repeat the process with the third block. Now that we have all the blocks decrypted, let's decode them from bytes to show the plaintext again. So think it like that. An attacker has the cookie that we encrypted, and the attacker sends it to us. We decrypt it, and we check if the user is admin. But there is a problem. The attacker can modify the ciphertext and influence the decryption to manipulate the plaintext data. For example, if the attacker changes the first byte of the ciphertext, in this case it increments the byte by 1, this change will propagate through the decryption of the first block until the plaintext. The plaintext will contain garbage now, because that single byte changed the whole decryption of the first block. But also, this change in the first byte of the ciphertext also affected the second block. That is because the ciphertext of the first block is directly used in the XOR operation of the second block. So now, instead of having a byte 30, we'll have byte 31. We changed the first byte of the plaintext from 0 to 1. It turns out that we can fully control the plaintext decryption from the second block onwards by changing the ciphertext. So, instead of changing the first byte, let's change this other byte. We increment it by 1. The change is propagated to the second block. And now we have isAdmin equals to 1. Obviously, we have the first block completely messed up. If we have an application that is fault tolerant to having some parts of the data corrupted, then we can abuse that. Let's go back to our challenge and see what we can do. Obviously, we cannot be sure if this technique works or not until we try. Also, we don't know what to modify. We could modify multiple bytes at the same time, for example. But as we cannot control that, we can try with a single bit flipping at a time for every byte. Let's create a simple script that does the job. But before, let's see what happens if we send an invalid cookie to the server. If we grep by the word decode, we see cannot decode the cookie. So basically what we need to do is first obtain a fresh cookie by sending a request. I will use the request library from Python. Then we define the URL for the challenge. Now we create a function that it is called bitFlipAttack, and then we do the request to get the outName cookie. We need to add the allowed redirects to false because the server responds with a redirect and it tries to get the cookie from the redirected page. And that page doesn't contain the cookie. Let's execute that. It prints our new fresh cookie. With that, we need to bit flip this cookie. We can create a method generateCookies that receives the original cookie and returns a list of all possible cookies bit flipped. We need to decode the cookie from base 64, and if you remember, it was encoded twice. Then we create an array that will contain all the bit flipped cookies, and we iterate for every byte in the decoded cookie. For every byte in the cookie, we will flip every bit and store it in the cookies array. In a byte, we have 8 bits, so we iterate from 0 to 8. We need to flip the byte. So let's define a function that receives a byte and the bit position to flip and returns the byte flipped. Now let's use it to generate the 8 flips for every byte. Then we create our modified cookie by getting the original cookie up to the byte modified. Then we add the byte that we flipped, and then we add the rest of the bytes. We base 64 encode the cookie twice, we add it to the cookies array, and finally we return the array. Next, we use the function we just created to create the list of flipped cookies from the original cookie. And we can send the request with every cookie we have generated. If the response of the request doesn't contain the string cannot decode cookie, then we stop and print the response. Let's execute our script. What we see now are the prints for the response object, but they contain the string cannot decode the cookie, so the content is not print. After some time, we will see our flag. Now we have our flag. I hope the video was helpful. Thanks a lot for watching.